Howdy y'all, let's talk about gas laws. This is actually going to be a review from first year chemistry most of the way, but there's going to be pressure, volume, number of particles, and temperature, right? Remember those? P, V, N, and T. This is N for the number of moles. If we know one of them is going to be changing, we can actually predict based on mathematical equations what the others are going to do, and that's what the gas laws help predict. There's going to be an issue because we're going to run into an issue with the real and the ideal gas. Real gases are the real world gases, and the ideal gas is how if they behaved perfectly. If we assumed these two things, if the particles were points in random motion and that they didn't interact at all. They're not exactly true, but if assuming this will actually give us some very surprisingly accurate results. So the first one is going to be Boyle's law, and that's going to be pressure and volume related to each other in an inverse way. I mean, as pressure goes down, the volume will go up. Or if the volume goes down, the pressure will go up. I can feel the pressure. So that's actually something that you see a lot, and especially in a water bottle I just showed you. The pressure can build up so much that it pops the cap off. You guys have probably seen that before. Remember, you boil peas and vegetables. We can show graphically when we see this that it will appear as an exponential decay. Then that's the type of graph you would see. So if you actually took the inverse of that, of one of those data points of pressure, if you took the reciprocal of all of those and just kind of flipped them and took 1 over those values and kept the same data, you would get a straight line instead. You see that, you're going to see that in college a lot too, that mathematical relationship. So here's the Boyle's law is actually the one that follows the ideal gas law, or all ideal gases obey Boyle's law. That's how we really base that off of. And you can see that all of these gases are behaving just a little bit off from the perfect value. And it looks like a lot in this graph, but if you really examine the scale here, the ideal gas isn't. It's actually a pretty insignificant amount. We can show it in vector form like this one. If we decrease the volume, we're actually increasing the number of collisions with the container. So that's how you would see it in vector form with all the little arrows. Remember that it's the direction and the magnitude of the arrows. One thing I've failed to point out is that there's Boyle's law is actually P1 V1 over P equals P2 V2. So this would be my initial condition. This would be my final condition. Charles' law is the direct relationship between volume and temperature, and we remember this by Charlie Brown's Christmas is on TV, and that's actually how these hot balloons work. If we increase the temperature of the gas molecules, the volume will actually increase and the balloon will get bigger and bigger and bigger. And that's how they inflate those balloons. To avoid getting a bunch of mathematical errors, you need to convert your temperatures to Kelvin always, please. That way we have an absolute scale, and then we won't get any negatives or zeros in our denominators, which would be bad. So, and like I said, it's on an absolute scale, because as the temperature decreases down, the volume will decrease down, and they would actually get to a point where we would get to a 0 here. This should be an open point because you can't actually get to absolute 0, because that's when nothing would have no heat at all, and molecules would not have any heat. So now let's look at Avogadro's law, where Avogadro had was did his work using gases. So he was working with the number of molecules, and he noticed that if we kept them all the same pressure and volume and temperature, that they would all have the same number of particles or the same number of molecules. And that's how he was able to come up with this idea of the mole. So even though they're not all the same size, if you let's just assume that they're all the same size. We had three different containers. The only difference is that they have different identities. The pressure, volume, and temperature are all the same. Then they would actually all have the same number of molecules. So that's Avogadro's law. The amount of the moles and the amount of the volume will always be directly related as well. So that's how they would be directly related, and also the pressure would be directly related, which isn't shown here. Gay-Lussac's laws with pressure and temperature. Again, remember the temperature's got to be in Kelvin, and that will be a direct relationship as well. All of them are going to be direct except for Boyle's law, which is indirect or inverse. So now, and you see this graph right here that just travels up in a nice little line. And your memory trick for that is Gale drives a PT Cruiser. We can put them all together using the combined gas law, which is just PV over T, or peas and vegetables on the table, with Boyle's law, Charles' law, and Gay-Lussac's law all mixed together. When we combine Boyle's, Charles, and Avogadro's law, we get the ideal gas law. So that would be PV equals nRT, or perv nert. And R is that proportionality constant. When you plug in all these values and all this data, for your math to actually work right, you need a little fudge factor, and that's what that value of R is. The value of R is given to you on your formula chart, and it's easy because there's three different values though, but because there's three different units of pressure. So depending on what unit of pressure that was given to you in the problem would depend on which value of R you would use. Most commonly you'll see this one right here, 0.08206. So the key to remembering all of these gas laws is to just remember the ideal gas law, okay? That's really all you got to remember, and that's actually given to you on your formula chart. That's awesome, PV equals nRT. And when you do that, it just put everything that's changing on one side and everything that's constant on the other. And then just eliminate stuff that's constant and keep the stuff that's changing. And then set them equal to each other, and you'll have your equation that you need to use. So I'll show you what I mean. If P and V change, or pressure and volume change, and the others are constant, I put PV over here equals nRT. And then I'm just going to cross out nRT because it's constant. And I'll write it again as my final value here, and that's PV equals nRT, but I'll cross these out. So now I'll set these two values equal to each other. And so I end up with this equation here, which is Boyle's law. Peas and vegetables on the table. No, just we boil peas and vegetables. That's right. So let's do an example. You can actually identify these gas law equations by if it actually says gas, or if it starts throwing a lot of numbers at you in one problem, that's probably it's going to be a gas law question. What the best way to do, because you get a lot of numbers when you do these, is to just start underlining them, the known numbers, so it's easy to see when you go back to it, and then start just writing them down. Write down the known information. So I jot down that 1.5 atmospheres and 298 Kelvin. Notice how I just switched to Kelvin automatically. It's a great habit. Now I know I'm going to be looking for a pressure, and I know a temperature. So it's going to give me uh, pressure and temperature. So I'm able to find out using the trick I just showed you. I can just know that I'm going to use Gay-Lussac's law uh, because it's got a PT cruiser. And when I do that, I just put everything on I put my unknown information on one side and my known information on the other. And then it's just calculator work. Just put it in the calculator and you get your answer. You might see a question here where it says it's going to at STP instead. So I'll still write down my known information, and that's going to be my initial values here, and I'll move my picture. And I'll have everything written down. But when I get to STP, remember that means standard temperature and pressure, and that one's on your formula chart too. So great! Standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. So I go ahead and write those down and convert temperature to Kelvin right away. And I find out that my missing value is going to be my volume. Now I know I'm just going to use the combined gas law and then put everything on, separate my known and my unknowns, and then plug in my values, and then I'm just going to get my answer. If you get a question like this, it is going to ask you the volume. It's going to give you the volume, and it's going to give you the pressure and the temperature, and want to know the mass instead. Well, how do we find mass? Mass wasn't on one of those values, but the number of particles was. So that means I know the moles. You can find the number of moles and then just convert moles to grams. So, and it's given you kilopascals. It's not going to be on the AP test. You'll still run into it. So let's go ahead and use it. So I give it to you in kilopascals, and we divide by 101.3 to get it to atmospheres. Because we like working in atmospheres better. Then we have volume as 50 liters, and then our unknown number of moles. And I know it's going to be an ideal gas equation, so I pick my value of R that has the atmospheres. And then I'm going to convert my temperature to Kelvin. And then I'm going to have my pressure and volume and temperature. PV equals nRT. Plug in my values. And find the N is 31.5 moles. That doesn't give me the answer. Well, I don't think that'll even earn you a half point on the AP test. So why don't we go ahead and convert moles to grams? That's so much easier. And then we get all our points. We find out that there's 1 kilogram of oxygen. It's great.